Hi, I am Arib. You are watching my YouTube channel. Electric locomotive. Definition: an electric locomotive is a locomotive powered by electricity from overhead lines, a third rail or onboard energy storage such as a battery or a supercapacitor. Locomotives with onboard fueled prime movers, such as diesel engines or gas turbines, are classed as diesel electric or gas turbine electric and not as electric locomotives, because the electric generator motor combination serves only as a power transmission system. Electric locomotives benefit from the high efficiency of electric motors, often above 90%, not including the inefficiency of generating the electricity. Additional efficiency can be gained from regenerative braking, which allows kinetic energy to be recovered during braking to put power back on the line. Newer electric locomotives use AC motor inverter drive systems that provide for regenerative braking. Electric locomotives are quite compared to diesel locomotives since there is no engine and exhaust noise and less mechanical noise. The lack of reciprocating parts means electric locomotives are easier on the track, reducing track maintenance. Power plant capacity is far greater than any individual locomotive uses, so electric locomotives can have a higher power output than diesel locomotives, and they can produce even higher short-term surge power for fast acceleration. Electric locomotives are ideal for commuter rail service with frequent stops. Electric locomotives are used on freight routes with consistently high traffic volumes or in areas with advanced rail networks. Power plants, even if they burn fossil fuels, are far cleaner than mobile sources such as locomotive engines. The power can also come from low-carbon or renewable sources, including geothermal power, hydroelectric power, biomass, solar power, nuclear power, and wind turbines. Electric locomotives usually cost 20% less than diesel locomotives. Their maintenance costs are 25 to 35% lower and cost up to 50% less to run. The chief disadvantage of electrification is the high cost for infrastructure, overhead lines or third rail, substations, and control systems. The impact of this varies depending on local laws and regulations. Interferes with electrification. Higher property taxes are imposed on privately owned rail facilities if they are electrified. The EPA regulates exhaust emissions on locomotive and marine engines, similar to regulations on car freight truck emissions, in order to limit the amount of carbon monoxide, unburnt hydrocarbons, nitric oxides, and soot output from these mobile power sources. Because railroad infrastructure is privately owned in the US, railroads are unwilling to make the necessary investments for electrification. In Europe and elsewhere, railway networks are considered part of the national transport infrastructure, just like roads, highways and waterways, so are often financed by the state. Operators of the rolling stock pay fees according to rail use. This makes possible the large investments required for the technically and, in the long term, also economically advantageous electrification. History. The first known electric locomotive was built in 1837 by chemist Robert Davidson of Aberdeen, and it was powered by galvanic cells, batteries. Davidson later built a larger locomotive named Galvani, exhibited at the Royal Scottish Society of Arts exhibition in 1841. The 7-ton vehicle had two direct drive reluctance motors, with fixed electromagnets acting on iron bars attached to a wooden cylinder on each axle, and simple commutators. It hauled a load of 6 tons at 4 miles per hour, 6 kilometers per hour, for a distance of 1.5 miles, 2.4 kilometers. It was tested on the Edinburgh and Glasgow Railway in September of the following year, but the limited power from batteries prevented its general use. It was destroyed by railway workers, who saw it as a threat to their job security. The first electric passenger train and first electric locomotive powered by a generator was presented by Werner von Siemens at Berlin in 1879. The locomotive was driven by a 2.2 kilowatts series wound motor, and the train, consisting of the locomotive and 3 cars, reached a speed of 13 kilometers per hour. During 4 months, the train carried 90,000 passengers on a 300-meter-long, 980-foot circular track. The electricity, 150-volt DC, was supplied through a third insulated rail between the tracks. A contact roller was used to collect the electricity. The world's first electric tram line opened in Lichterfeld near Berlin, Germany, in 1881. It was built by Werner von Siemens. Electric Railway opened in 1883 in Brighton. Also in 1883, Mödling and Hinterbrühl. Tram opened near Vienna in Austria. It was the first in the world in regular service powered from an overhead line. 5 years later, in the US, electric trolleys were pioneered in 1888 on the Richmond Union Passenger Railway, using equipment designed by Frank J. Sprague. Much of the early development of electric locomotion was driven by the increasing use of tunnels, particularly in urban areas. Smoke from steam locomotives was noxious, and municipalities were increasingly inclined to prohibit their use within their limits. The first electrically worked underground line was the City and South London Railway, prompted by a clause in its Enabling Act prohibiting the use of steam power. It opened in 1890, using electric locomotives built by Mather and Platt. Electricity quickly became the power supply of choice for subways, abetted by Sprague's invention of multiple-unit train control in 1897. Surface and elevated rapid transit systems generally used steam until forced to convert by ordinance. The first use of electrification on an American main line was on a 4-mile stretch of the Baltimore Belt Line of the Baltimore and Ohio Railroad, B&O, in 1895, connecting the main portion of the B&O to the new line to New York through a series of tunnels around the edges of Baltimore's downtown. Parallel tracks on the Pennsylvania Railroad had shown that coal smoke from steam locomotives would be a major operating issue and a public nuisance. 3 BO plus BO units were initially used, the EL1 model. At the south end of the electrified section, they coupled onto the locomotive and train and pulled it through the tunnels. Railroad entrances to New York City required similar tunnels, and the smoke problems were more acute there. A collision in the Park Avenue Tunnel in 1902 led the New York State Legislature to outlaw the use of smoke-generating locomotives south of the Harlem River after 1 July 1908. In response, electric locomotives began operation in 1904 on the New York Central Railroad. In the 1930s, the Pennsylvania Railroad, which had introduced electric locomotives because of the NYC regulation, electrified its entire territory east of Harrisburg, Pennsylvania. The Chicago, Milwaukee, St. Paul, and Pacific Railroad, the Milwaukee Road, the last transcontinental line to be built, electrified its lines across the Rocky Mountains and to the Pacific Ocean starting in 1915. A few East Coast lines, notably the Virginian Railway and the Norfolk and Western Railway, electrified short sections of their mountain crossings. However, by this point electrification in the United States was more associated with dense urban traffic, and the use of electric locomotives declined in the face of dieselization. Diesel shared some of the electric locomotive's advantages over steam and the cost of building and maintaining the power supply infrastructure, which discouraged new installations, brought on the elimination of most mainline electrification outside the Northeast. Except for a few captive systems, example the Desert Power Railroad, by 2000 electrification was confined to the Northeast Corridor and some commuter service. Even there, freight service was handled by diesel. Development continued in Europe, where electrification was widespread. 1500-volt DC is still used on some lines near France, and 25 kV 50 Hz is used by high-speed trains. Direct and alternating current, the most fundamental difference lies in the choice of AC or DC. The earliest systems used DC, as AC was not well understood and insulation material for high-voltage lines was not available. DC locomotives typically run at relatively low voltage, 600 to 3000 volts. The equipment is therefore relatively massive because the currents involved are large in order to transmit sufficient power. Power must be supplied at frequent intervals, as the high currents result in large transmission system losses. As AC motors were developed, they became the predominant type, particularly on longer routes. High voltages, tens of thousands of volts, are used because this allows the use of low currents. Transmission losses are proportional to the square of the current. Example, twice the current means 4 times the loss. Thus, high power can be conducted over long distances on lighter and cheaper wires. Transformers in the locomotives transform this power to a low voltage and high current for the motors. A similar high voltage, low current system could not be employed with direct current locomotives because there is no easy way to do the voltage current transformation for DC so efficiently as achieved by AC transformers. AC traction still occasionally uses dual overhead wires instead of single-phase lines. The resulting three-phase current drives induction motors, which do not have sensitive commutators and permit easy realization of a regenerative brake. Speed is controlled by changing the number of pole pairs in the stator circuit, with acceleration controlled by switching additional resistors in or out of the rotor circuit. The two-phase lines are heavy and complicated near switches, where the phases have to cross each other. The system was widely used in northern Italy until 1976 and is still in use on some Swiss rack railways. The simple feasibility of a fail-safe electric brake is an advantage of the system, while speed control and the two-phase lines are problematic. Rectifier locomotives, which used AC power transmission and DC motors, were common, though DC commutators had problems both in starting and at low velocities. Today's advanced electric locomotives use brushless three-phase AC induction motors. These polyphase machines are powered from GTO, IGCT or IGBT-based inverters. The cost of electronic devices in a modern locomotive can be up to 50% of the cost of the vehicle. Electric traction allows the use of regenerative braking, in which the motors are used as brakes and become generators that transform the motion of the train into electrical power that is then fed back into the lines. This system is particularly advantageous in mountainous operations, as descending locomotives can produce a large portion of the power required for ascending trains. Most systems have a characteristic voltage and, in the case of AC power, a system frequency. Many locomotives have been equipped to handle multiple voltages and frequencies as systems came to overlap or were upgraded. American FL9 locomotives were equipped to handle power from two different electrical systems and could also operate as diesel electrics. While today's systems predominantly operate on AC, many DC systems are still in use. Example, In South Africa and the United Kingdom, 750 volt and 1500 volt. Netherlands, Japan, Ireland, 1500 volt. Slovenia, Belgium, Italy, Poland, Russia, Spain, 3000 volt. And Washington, D.C., 750 volt. Power transmission, electrical circuits require 2 connections, or for 3-phase AC, 3 connections. From the beginning, the track was used for one side of the circuit. Unlike model railroads, the track normally supplies only one side, the other side of the circuit being provided separately. Overhead lines, railways generally tend to prefer overhead lines, often called catenaries after the support system used to hold the wire parallel to the ground. 3 collection methods are possible. Trolley pole, a long flexible pole, which engages the line with a wheel or shoe bow collector, a frame that holds a long collecting rod against the wire. Pantograph, a hinged frame that holds the collecting shoes against the wire in a fixed geometry. Of the 3, the pantograph method is best suited for high-speed operation. Some locomotives use both overhead and third rail collection, example British Rail Class 92. In Europe, the recommended geometry and shape of pantographs are defined by standard EN 50367 IEC 60486. Third rail, mass transit systems and suburban lines often use a third rail instead of overhead wire. It allows for smaller tunnels and lower clearance under bridges, and has advantages for intensive traffic that it is a very sturdy system, not sensitive to snapping overhead wires. Some systems use 4 rails, especially some lines in the London Underground. One setback for third rail systems is that level crossings become more complex, usually requiring a gap section. The original Baltimore and Ohio Railroad electrification used a sliding pickup, a contact shoe, or simply the shoe in an overhead channel, a system quickly found to be unsatisfactory. It was replaced by a third rail, in which a pickup rides underneath or on top of a smaller rail parallel to the main track, above ground level. There are multiple pickups on both sides of the locomotive in order to accommodate the brakes in the third rail required by track work. This system is preferred in subways because of the close clearances it affords. Driving the wheels. During the initial development of railroad electrical propulsion, a number of drive systems were devised to couple the output of the traction motors to the wheels. Early locomotives often used jackshaft drives. In this arrangement, the traction motor is mounted within the body of the locomotive and drives the jackshaft through a set of gears. This system was employed because the first traction motors were too large and heavy to mount directly on the axles. Due to the number of mechanical parts involved, frequent maintenance was necessary. The jackshaft drive was abandoned for all but the smallest units. When smaller and lighter motors were developed, several other systems were devised as the electric locomotive matured. The Bouchley drive was a fully spring-loaded system, in which the weight of the driving motors was completely disconnected from the driving wheels. First used in electric locomotives from the 1920s, the Bouchley drive was mainly used by the French SNCF and Swiss Federal Railways. The quill drive was also developed about this time and mounted the traction motor above or to the side of the axle and coupled to the axle through a reduction gear and a hollow shaft. The quill flexibly connected to the driving axle. Locomotive used a quill drive. Again, as traction motors continued to shrink in size and weight, quill drives gradually fell out of favor in low-speed freight locomotives. In high-speed passenger locomotives used in Europe, the quill drive is still predominant. Another drive was the bipolar system, in which the motor armature was the axle itself. the frame and field assembly of the motor being attached to the truck, bogie, in a fixed position. The motor had two field poles, which allowed a limited amount of vertical movement of the armature. This system was of limited value since the power output of each motor was limited. The EP2 bipolar electrics used by the Milwaukee Road compensated for this problem by using a large number of powered axles. Modern freight electric locomotives, like their diesel-electric counterparts, almost universally use axle-hung traction motors, with one motor for each powered axle. In this arrangement, one side of the motor housing is supported by plain bearings riding on a ground and polished journal that is integral to the axle. The other side of the housing has a tongue-shaped protuberance that engages a matching slot in the truck, bogie, bolster, its purpose being to act as a torque reaction device, as well as support. Power transfer from the motor to the axle is effected by spur gearing, in which a pinion on the motor shaft engages a bull gear on the axle. Both gears are enclosed in a liquid tight housing containing lubricating oil. The type of service in which the locomotive is used dictates the gear ratio employed. Numerically high ratios are commonly found on freight units, whereas numerically low ratios are typical of passenger engines. Wheel arrangements. The white notation system for classifying steam locomotives is not adequate for describing the variety of electric locomotive arrangements, though the Pennsylvania Railroad applied classes to its electric locomotives as if they were steam. For example, the PRRGG1 class indicates that it is arranged like 2460 class G locomotives coupled back to back. UIC classification system was typically used for electric locomotives, as it could handle the complex arrangements of powered and unpowered axles and could distinguish between coupled and uncoupled drive systems. Types. An electric locomotive can be supplied with power from rechargeable energy storage systems, such as a battery or ultracapacitor-powered mining locomotives, a stationary source, such as a third rail or overhead wire, a mixture of both. The distinguishing design features of electric locomotives are the type of electrical power used, AC or DC, the method of storing, batteries, ultracapacitors, collecting, transmission, electrical power, and or mixed method, the means used to couple the traction motors to the driving wheels, drivers.